Hello and welcome to your last pre-calculus lesson. This lesson is from 11.3, which is limits. We're going to look at limits algebraically and graphically. And this is pre-calculus in the truest sense because this will actually be your first unit in calculus. Well, after review maybe, will be a unit on limits. There's a decent amount of information, and so I'm going to try and go as quickly as possible without rushing too much for you. So the limit notation, I believe you're already familiar with. Limit notation says the limit of f of x as x approaches c is L. You can also switch those two phrases and read that the limit as x approaches c of f of x is L. And this just means that as x horizontally, if you're looking as x is headed towards c, the y value that the function approaches would be the y value of L. The limit of a function refers to the value that it approaches, but not the actual value of a function. So, for instance, here if I look as x approaches 2, it looks from the left and from the right, it looks like the function is headed toward 2, right? The y value of 2. So the function is approaching that y value of 2, which means that limit is 2, even though the actual value here, because I have a dot, f of 2 is actually 1, but the limiting value would still equal 2 because that's okay. So let's look at an example. Let's pick a couple points here to look at. So let's try 1. So I believe that you're familiar with these superscripts, but just in case not, if I look at as x approaches 1, the plus sign superscript means from the right. Now, incidentally, if this said y approaches 1 with a superscript of a plus sign, then that would be y approaches 1 from above. Because you're looking at a y value, but we won't be looking at that. We'll just have x values here. So as x approaches 1, from the right is what that plus sign means. And so I can look in the neighborhood of x equals 1. I don't care about the junk way off to the right, but just in the neighborhood of x equals 1. As it approaches x equals 1 from the right, it looks like it's headed toward the y value of 1. The next one says as x approaches 1 from the left. Well, as x approaches 1 from the left, the y value that the function is 0. The next one is the overall limit as x approaches 1 of f of x. And for the overall limit to exist, the left-hand limit and the right-hand limit have to be the same. In this case, 1 and 0 are not the same number, so I could say that this overall limit does not exist, and we would just write DNE for does not exist. And then f of 1 is saying, yeah, but what's the actual value of the function at x equals 1? And so we would find the closed dot, and we would say the actual value of the function there is 1. So that's one example. And then if we want to do one more, if we look at 3, the limit as x approaches 3 from the right would be 2. The limit as x approaches 3 from the left of f of x would also be 2, which means since those are the same, that the overall limit is 2, and f of 3 is, you guessed it, 2. And since those are all the same number, that actually means that the function is continuous at x equals 3. That's our official definition of continuity that I'm going to give you next year, or that Mr. Evans will give you next year. And that just means that you can draw it without picking up your pencil, because the value coming in from the left is the same as the value of the function is the same as the value on the right-hand side. Okay, so now we're going to try drawing a function that satisfies all of these conditions. And so I'd like you to try that on your own and pause the video, and then I'll do it with you in 3, 2, 1. All right, let's see how we can do. So first off, I'm going to look at the ones that are that have no ambiguity or no wiggle room, and that would be the points. So we did a little bit of this in chapter 1, and I think that you should be okay with it, but just to make sure, we're going to do this example anyway. So f of 1 is 4, so got to put a dot there. And f of 2 is 0, means that I've got to stick a dot there. And then now I can start looking at the limits and see what I can do with these. And sometimes you have more options than just the function that I would be drawing. So here it says the limit as x approaches 2 from the left is 3. So, but I know the actual value is 0. So I know that I've got to be headed there from the left. And so I'm just going to mark that in. I don't know what else I need to put, so I'm just going to leave that there with a tiny little tail so that I knew that that was the left. The limit as x approaches 2 from the right is 2. So I'm going to head to 2 from the right. And again, I'll fill in the rest later, but I'm not really sure what else is going on, so I'll just leave that. The limit as x approaches 1, this would be the overall limit because there's no superscript there, of f of x is -1. So again, the actual value was 4, but I know that the limit is -1. So now I can actually go ahead and draw that in. And I know that coming off on the other side that it also has to be approaching -1 from both directions, since this is the overall limit. So that one's done. And now we just have 2 left. The limit as x approaches -infinity of f of x is 3. So that means that this must turn back up. Limits at infinity are synonymous with horizontal asymptotes if they are finite limits. So because this limit is 3, which is a finite limit, then that means that the horizontal asymptote on that side would be y equals 3. But last but not least, we've got that the limit as x approaches positive infinity of f of x is -infinity. So that means as x heads toward positive infinity, which would be to the right, the function is going to head towards -infinity and beyond. And the shape of that doesn't really matter because it doesn't tell us. And so this would be one example of a graph that we could draw. And this is obviously a crazy graph because I wanted to illustrate a lot of properties for you. But this graph would fulfill all of the properties I could do. Okay, so that was limits graphically. Now we're going to look at limits algebraically. So here are some steps if you are trying to evaluate limits algebraically. Number 1, try direct substitution. If you can simply substitute in the value and get a number, then you are done. If you get 0 divided by some number, that is okay, because 0 divided by some number equals 0, and so you're done because the limit would be equal to 0. However, if you get a number divided by 0, no, that is not okay. And that would mean that the limit either does not exist or is infinity or is -infinity if you get this at some number over 0. And so infinity and -infinity also mean that a finite limit does not exist. So really does not exist as kind of a more general answer that would work even if the answer was infinity or -infinity. You could say does not exist, depending on the textbook and what it's asking of you. And then last but not least, if you get 0 over 0 or infinity over infinity, then that's inconclusive because there are different sizes of infinities. And so I'm going to show you why on the next page, which is super cool. And so if you get 0 over 0, chances are it's either a hole in the function or a fundamental trig limit. which we'll do at the end. And so what you would do is, if there's a hole in the function, you would remove the hole and then go back to step 1 and try direct substitution. Step 3, which is other options, I don't think that you have any of those in this lesson, but you will see them next year, are some other things that you can do to try to evaluate limits. So, and for those of you that are Mean Girls fans, if the function does not approach a finite value, what can we say about the limit? The limit does not exist, right? And that's what we were just talking about here. Okay, so I want to show you just examples of why infinity over infinity or 0 over 0 means that you have to do more. So for instance, if I had the, if I was looking at the limit as x approaches positive infinity, which would be the same as looking for, if there is one, a horizontal asymptote of x minus 3 over x plus 2. Then if you were looking for the horizontal asymptotes of that function, you would say, oh, that's Bobo-Bot and that's DC. And so you would look at the degrees and you would say, oh, the degrees are the same, they're both 1. So we would divide the leading coefficients, 1 and 1, and we would say that that limit is 1. However, if I was trying direct substitution, quote unquote, by substituting in infinity, quote unquote, I'd get infinity minus 3 over infinity plus 2, which is infinity over infinity, right? And I know that infinity is not a number, so if that weirds you out, which I kind of hope it does, you can always try 100. 100 is not very close to infinity, but it's going to be close enough for us. And if I substitute in 100, I would get 97 over 102, and I can kind of see that that number would be approaching, or would be getting closer and closer to 1. So I can either substitute a value that's close and then guess from there, or you could use Bobo-Bot and that's DC. However, if we look at the limit as x approaches infinity of x minus 3 divided by x squared plus 4, if I do a direct substitution, it's infinity over infinity, right? You're still going to get an infinity over an infinity. However, I know that this limit is 0 from Bobo-Bot and that's DC because the degree is bigger on the bottom. And if I take the limit as x approaches infinity of x squared plus 4 over x minus 3, all of a sudden now the degree is bigger on the top, which means that that there is no horizontal asymptote, and so there is no finite limit. Turns out this limit would be infinity. So all 3 of these examples by direct substitution would be examples of cases where we would see infinity over infinity, but they have 3 different results: 0, a non-zero finite number, and infinity. Okay, some properties of limits. Limits can be added, subtracted, multiplied by a constant, multiplied by each other, and divided as long as the denominating limit is not 0. So all of those properties that you would think that you can do with limits, you can. So for example, if the limit as x approaches c of f of x is 4, and the limit as x approaches c of g of x is -3, then the limit as x approaches c of their sum would simply be the sum of the limits, 4 plus -3, which would equal 1. And the limit as x approaches c of x times g of x, well, as x approaches c, x would approach c, right? I just said that. And then as x approaches c, g of x equals -3. And so this would be -3c is what that one would approach. And so you can mess around with all those properties of limits. And I know that that was very quick, but I think that will suffice for what you need. And so let's look at some practice. First off, If you want to try these on your own, go ahead and pause, or we're going to do them together in 3, 2, 1. All right, first one, limit as x approaches 5 of x squared minus 13. First off, we would always try direct substitution. So if I directly substitute, does that create a problem? Does it create a 0 in the denominator or something wonky like that? No, it doesn't. So this would just be 5 squared minus 13, which is 12. And that's it, you're done. Let's do the next one. The limit as x approaches 3 of x squared minus 9 over x minus 3. So I'll try direct substitution and say 3 squared minus 9 over 3 minus 3. And I can see already that this is going to be ugly because I'm going to get a 0 on the bottom, which I know is not allowed. And 3 squared minus 9 is 0 on the top as well. So, maybe I should look for a hole in the function, right? This is not okay to leave it like that because you're not allowed to divide by 0. So instead, let's look at this function again. X squared minus 9 factors into x minus 3 times x plus 3. And so since I have the same factor on the top and the bottom, there's a hole in the function at x equals 3, and I can cross that out, meaning that that is inconsequential to what the function looks like, except for that there's a hole there, which would give us that this graph would look exactly like the graph of y equals x plus 3, except for that when I get to x equals 3, that there would be a hole in the function at x equals 3, because that was the value that would produce the 0 on top and bottom. So now it's easy to look at this limit because I can either consider the graph or I can direct substitute into what's left over. So I can substitute this value now into the piece that's left over after I took out the hole, and that would be 3 plus 3, and so I would get a limiting value of 6. I can see from my graph that, yep, the y value that it's approaching on both sides is 6, even though there's a hole in the function. Here's some more practice. So try these on your own, please. Pause the video, and then we'll just check your answers in 3, 2, 1. All right, here you go. Check your answers and see if you got it right. First one, 0 over -4, which is just 0. Third one, 16 minus 16, which is just 0, which is fine. The answer is 0. Second one, 4 divided by 0 means that that limit does not exist. Now, more specifically, we could see if there is a limit at of infinity or of negative infinity. We know from graphing rational functions that x minus 2 on the bottom means that there would be a vertical asymptote at x equals 2, and our 0 would be at x equals -2. And I know that if I substitute in a y-intercept, I would, so 0 for x, I would get -1 for y. And from Bobobot and DC, I can see the horizontal asymptote is going to be y equals 1. So all this stuff that we did, that was section 2.6, I believe, where we were graphing rational functions. But all the things that we did graphing rational functions, if you remember them, it makes limits so much easier, because if you know what this graph looks like, then you know that the limit from the right as x approaches 2 would be positive infinity, and the limit from the left as x approaches 2 would be negative infinity, and so the overall limit does not exist. All right, let's try these. And again, feel free to use your knowledge of the graph of this function. So try it on your own, and then we'll go over answers in 3, 2, 1, 0. Okay, let's see how you did. So the first one said, as x approaches 5 from the left. I know that this is just a transformation of the reciprocal function. It's been vertically stretched by 2, and the x minus 5 just shifts it to the right 5 units. So I know that this function is going to look kind of like the sketch that I have there. So as x approaches 5 from the left, that y value would be approaching negative infinity. However, as x approaches 5 from the right, that would be positive infinity, and so the overall limit does not exist. The other way that you can do this, other than graphing it, is if it says, for instance, 5 from the right, I can pick a value a tiny bit to the right of 5. So 2 over 5.01 minus 5, or 5.1 would probably work as well. And so that would be 2 divided by 0.01, which would be 200. And we would say that 200 is obviously, well, maybe not obviously, but is approaching infinity. And we take a few liberties with that, how close 200 actually is to infinity there. You can do the same thing with from the left. You could say 2 divided by 4.9, right? Pick a value to the left of 5, but just a little bit. 4.9 minus 5, and then that would be 2 divided by negative 0.1. So that would be negative 20. And again, saying that negative 20 is close to negative infinity is a bit of a stretch, but that'll help you figure it out maybe. And then let's look at the last one here. The limit as x approaches 5 of negative 2 divided by x minus 5 quantity squared. So I wanted to give you an example, lest you think that all of these that have a denominator issue are just going to be D&E. Here, if I put in 5 for direct substitution, I do get negative 2 over 0. And so I can see, yeah, that's going to be infinity, negative infinity, or it does not exist. However, if I put in 5.1, then that would be negative 2 divided by 0.1 squared, which would be negative 2 divided by 0.01, which would be negative 200. And if I put in 4.9, 4.9 minus 5 is negative 0.1, but when you square it, you're going to get the same value as I did there. So you're going to get negative 200 on both sides. And that's because this graph, other than the fact that my y-intercept I graphed was just incorrect. I wasn't paying attention. Let's look. The actual y-intercept would be negative 220. So there you go. And so this graph actually looks something like that. And I can see that both of them, both of the limits on the left and right are headed towards negative infinity. And so I could say D&E because a finite limit does not exist. But more specifically, I could say negative infinity because both sides are headed toward negative infinity. And I have a little joke here for you. I'll give you a second to read it. I know you're laughing. It's a good one. Okay, last page. Fundamental trig limit. I am not going to prove this for you. I am going to just tell you this, and then you are going to believe me on this. So the fundamental trig limit, there are a couple of them, but the one that we're looking at says that the limit as x approaches 0 of sine x over x equals 1. So sine x we know oscillates. If I try direct substitution, I get 0 over 0, but there's no whole that I can take out here. So it's not anything that I could actually reason through. However, you can graph this function on your graphing calculator, and it looks like that, kind of, more or less. And so you can see that the limit as x approaches 0 is 1 of this function. And so we can use that to find limits of the examples like I have written down here. So in this case, this I could break up and look at a product, and I could say that this would be the function itself. So this would be the limit as x approaches 0 of, and then the function itself I'm going to break up into 2/3 and sine x over x. And then I'm going to evaluate each of those limits individually. So the limit as x approaches 0 of 2/3 is just 2/3 because that's a horizontal line. And the limit as x approaches 0 of sine x over x is 1 because of the fundamental trig limit, and I'd have 2/3 for the answer there. For the second one, I can't exactly do that with the second one because the 7 is inside, not on the outside. And so also the sine quantity is on the bottom, not the top. But I can say that this would be the limit as x approaches 0 of, and I'm going to do a little bit of hocus pocus here. I'm going to put sine 7x there, and I know that I could use the fundamental trig limit if this was not just x, but if it was 7x, because I would have the sine of 7x and 7x above and underneath each other, and so I could use the fundamental trig limit for that. The thing is, though, you can't just put a 7 there because that changes the value. So if I put a 7, I will compensate for that by putting a 1/7 there. So it's a little bit of hocus pocus, like kind of like completing the square. You put something that wasn't there and then you just compensate for it. And so in this case, if I multiply these individual limits, I would get 1/7 for the first one because that would just be a horizontal line at y equals 1/7. And now the second one here, because I have the same quantity on one side of the fraction as the argument of sine on the other side of the fraction, that limit is also going to be 1, because think about it, if the function approaches 1 and you flip it, it's still going to approach 1. It would approach 1 from the other direction. So if I was approaching 1 from below, now I might be approaching 1 from above, but it doesn't matter because I would still be approaching 1 there. And so that answer would be 1/7 times 1. Last but not least, if I had the limit as x approaches 0 of 3x plus sine x over x, then I would want to break this up into multiple fractions and say that this would be the limit as x approaches 0 of 3x over x, which is just 3, and sine x over x. And then I can use the property of limits that says that I can add the two limits. So the limit as x approaches 0 of 3, again, 3 would just be a horizontal line, and so that limit would be 3. And then the limit as x approaches 0 of sine x over x is 1, and then that would give me a limiting value of 4 there. So I hope that you have seen how to use the fundamental trig limit. That's it. Thanks for hanging in. I know it was a little bit long, but that was your last lesson. And you have 2 days to work on this and an extra day of review. So don't feel like you have to do your homework right now. You can save it for tomorrow. It's been a pleasure, and hope to see you at class awards, which is on Friday. Bye.